Okay, so I'm going to come up with a couple of these definitions here, several of them, and they're going to involve u, v, w, and z. And what I want u, v, w, and z to represent can be anything that's a real number, 2, a variable, x or y or whatever, or algebraic expressions. And so that can be just about anything you put together. Think of a polynomial like 2x squared plus 1. Also could be things like the square root of x plus 1, you know, all those kinds of algebraic expressions. So let these represent any of those. And so when I'm multiplying two ratios, two rational expressions that are ratios of numbers, variables, or algebraic expressions, basically all I do is I multiply the numerators together and the denominators together. And I also have to recognize that u or that v and z can't be 0. So you can't divide by 0. Now with the way multiplication works is in order for this to be 0, one of them has to be 0. So the domain restrictions of each of these individual terms applies to the product of those two ratios as well. Okay, so an example, let's say I have 6x over x minus 2, and I want to multiply that by x minus 3 over x squared. Basically, I put them together, and then I simplify. So the only thing I have in common here, I have an x in the numerator and an x squared in the denominator. So I can eliminate one of them and make that 6 times x minus 3 over x times x minus 2. So one of the x's canceled. Now I don't need any domain restrictions here because it's already implied that x should not equal 0, cannot equal 0, and everything else was the way it was originally. So no need to make domain restrictions. Now when I say simplify, if you read our book very carefully, you'll notice that there's a contradiction in how they want you to simplify things. They'll show you this in one of the earlier chapters, and when they say simplify, they mean multiply that out to get 6x minus 18 over x squared minus 2x, right? Expand it. And in a sense, that's simplifying because you're removing parentheses. But here, when they say simplify, they leave it in factors. And so from here on out, you can leave your terms as factors, because this will ultimately tell you more about the behavior of this expression than would be if you multiplied it out to the polynomial. So don't feel like you ever have to expand something like this. Certainly is not wrong if you do. According to the early definition of simplification in the book, of course you're simplifying it, but don't feel like you have to go beyond this. This is perfectly good. When we say simplify, we're trying to remove the common terms of the numerator and the denominator. Okay, let's have another example here. Now here I have 4 minus 2x times 2 plus x over 2 minus x. Now I'm talking about rational expressions, so remember that any expression that algebraic expression that you have can be made into a rational expression just by putting it over 1, right? So if I were to treat it like it's 4 minus 2x over 1, then what I need to do is just multiply out. Now notice what I did here. I didn't just multiply these two. Oftentimes, before you multiply, if you factor it, it'll be easier factoring something small than if you multiply these two together and then try and factor it. I mean, think about it. If 36 is 4 times 9, 4 is easier to factor, 9 is easier to factor than 36 by itself. So don't be too eager to multiply everything out. Keep things in terms of factoring, cancel out the factors, and then see where you can go from here. So in this case, we have a 2 minus x common to the numerator and the denominator. So those cancel out. We end up with a 1 in the denominator, which we don't have to write, and then we just pay attention to our domain restrictions. In this case, since we're eliminating this 2 minus x, we know we have a domain restriction that x does not equal 2, and so we write that down to keep the expressions the same. Okay, everybody up with me? Okay, so you try a few. Here's 2 to try. You with you? It may seem a little odd that you have an expression, -1, and you're putting restrictions on z. Well, what you're really saying is, what does this, how does this simplify? And it only simplifies to -1 if z doesn't have these values, right? Because let's say if z equals -8, then we have 0 and 0 here, so we have 0 over 0, which is indeterminate. That's not 1. 0 over 0 does not equal 1. So the only time that this equals -1 is if these conditions apply. You had a question, then?
Yeah, I was just going to ask, how would you do it if you didn't factor out a negative?
If you didn't factor out a -1, you'd have 8 minus z divided by z minus 8. You would know that that had to be 1, or a -1. Okay, so there's almost no way to do it. I mean, certainly recognize that whenever you have x minus y over y minus x, when you change these around, that equals -1. So you can make that leap once you recognize it, but strictly speaking, this is what you're doing. You're factoring out a -1. Okay? All right, so this isn't too different than what we've done last time when we were just simplifying rational expressions, right? The only difference is that we're going to remove the multiplication sign and put everything on the numerator or the denominator. And in fact, that's all it amounts to. Division works very similar, but we have one thing to watch for. So we can notate this as u over v divided by w over z. And that's the same u, v, w, and z that I had before. So this equals, notice what happened here, I took the reciprocal, so division is actually multiplying by the reciprocal. And so we can do this, and then of course combining them. But now we have 3 of these things that can't be 0. So when you look at the original, you see the z is in the denominator, so that can never be 0. V can never be 0. And then when we do this, we also see that W can't be 0 as well. So V, W, and Z can't be 0. U can be 0. Okay, so if U is 0 and Z, V, and W equal something else, then the whole expression equals 0, right? 0 divided by a number is a perfectly good number, 0. 0 is not, there's nothing wrong with 0. You just can't use it to divide. And so if I give you a simple example here where we have x over x minus 2 divided by x plus 1 over x plus 3, first thing we do is we make it into a multiplication problem. And notice there's no simplifying that I can do here. I have all unique factors and there's no factors that cancel, but I'm still writing an explicit domain restriction, because if I just look at this, the only implied domain restrictions here is that x does not equal 2 and x does not equal -1. But in my original problem, I have the implied domain restriction that x does not equal -3. So since that's no longer implied in what I've simplified to, I have to write that domain restriction out. Okay, everybody following? So those are still implied. All right, so let me take another example here. X squared minus 1 over x plus 2 divided by x plus 1 over x plus 2. Now, I'm doing two things at once here. The first thing I'm doing is I'm saying x squared minus 1 factors, and that goes to x plus 1 times x minus 1. And then I take the reciprocal of x plus 1 over x plus 2 and make it x plus 2 over x plus 1, and it's multiplying. So now I have three terms in the numerator, 2 terms in the denominator, and I can start looking for ones that are that I can cancel. So the x plus 1s cancel, the x plus 2's cancel, and so I still have to recognize the domain restriction here, but my expression is going to be equal to simply x minus 1. Okay, let's try a different example here. Okay, so what I'll take here with these two, notice what I'm doing along the way. I'm factoring and taking the reciprocal. So I recognize that 5x plus 5, I can factor out the 5. And then I'm multiplying that by x squared minus 2x minus 3, factored out as x minus 3 and x plus 1. Okay, so that comes from the denominator over here. And then I'm going to take this x squared minus 3 and factor out an x, and so I get in the denominator x times x minus 3. And then, of course, that 2x comes from the first term originally. All right, so now I can look around and see what can I cancel. And the x minus 3's cancel. And so I look at my original domain restrictions and see what's dropped out. Of course, x can't be 0. And so that takes care of this term of the numerator here. And it also takes care of the denominator here when x does not equal 0, which is implied here. But the ones that I've factored out, the x minus 3, that's a domain restriction that leads to x does not equal 3. And then this one originally was x minus 3 times x plus 1, this denominator. So I have to take into account x does not equal negative 1. Okay? So it takes an examination of the original problem to figure out where your domain restrictions are. You know, and if you factored it, where do those factors go? Okay, so of course, time for you to try one. Okay, so that's what you got. Okay, how about the next one? Yes.
For my final answer, I got x over x minus 1.
Okay. Okay, so yeah, I think you're right there. So I'll just kind of show the answer in the interest of time. X plus 5 times the denominator here. I'm going to take the x squared, factor the denominator, and then that's x over x minus 5, which is what you said. So that your domain restrictions here, remember you had x's in the denominator, so x can't be 0 here, and you also have an x plus 5 that you canceled out, so the x does not equal negative 5 is your other domain restriction. And then, of course, x can't equal 5, but that's implied already. Yes?
Wait, are there any domain restrictions for the first one?
It's only implied, right? Because here we have, if x equals 0, I have 0 divided by 0. And so that would be just x equals 0, but it's implied already. Okay? Okay, so let's talk about adding and subtracting rational expressions here. Now, my same definitions of u over w plus, or what u, v, and w are, if we're adding two rational expressions with the same denominator, we just add the numerators, keep the same denominator. Same thing with subtraction. If we have the same denominator, we keep the denominator and subtract the numerators. Okay, so we'll jump right in here. If we have x over 10 plus x plus 2 over 10, we just add all those things up and we get 2x plus 2 over 10. And now with adding them, you have to first fully expand it in order to be able to add common terms or like terms. And then when you are finished, now's the time to factor that. And it turns out we can factor it. And we get, factor out the 2, and 10 is 2 times 5, and so we get the answer x plus 1 over 5. Now I want to caution you, a lot of people make this mistake. When you have something like this, please don't do this. That's not right. Okay, that's just, And on a simple example, I know you all know that, but inevitably, when you're doing a hard problem and you get to an easy step, you make a simple mistake like that. So that's you always want to cancel by factors and not by individual terms. Okay, so here's one with a polynomial now in the denominator. We have n times n plus 2 in the denominator. So we write these out. Now notice what I'm doing here. In the subtraction, I'm writing the two numerators in parentheses and putting the subtraction sign in between them. That's really optional for the first one, but the second one, I really encourage you to do that because what's going to happen is, I know you know this, but it's one of those things that it's an easy mistake to make, is that negative applies to both the 1 and the negative 3n. And so when I distribute that, it's negative 1 plus 3n. And now I can add up all my like terms, and I get 2 plus n over n times n plus 2. And then, of course, I have the 2 plus n that will cancel, and I have 1 over n. And I keep my domain restriction that I lost by eliminating the n plus 2. And so n does not equal negative 2. Okay, so does everybody follow that one? Is that okay? All right, so nothing really conceptually that hard. Basically, avoid the mistakes by using parentheses. Now, if we have different denominators, we have to make a common denominator. And so what you want to do here is use the least common multiple. Now, I know sometimes it's a really tempting habit when you're when you're adding fractions. If you, let's say, add 2/5 plus 3/10, that you multiply the 5 times the 10, you get a common denominator of 50. I don't want you to do that. I want you to use the least common multiple because you're going to get expressions with far too high of a degree, and you're going to be factoring really ugly polynomials if you do that. So what I mean by that, a least common multiple, ignore the numerator for now. This is just what do I do with denominators. I notice when I factor the denominators, I notice that I have two factors of 2 in common. So I'm going to use that once, whatever you have in common, and then I'm going to use all my unique factors. And here I have a unique factor of 5 and a unique factor of 3. So 2 times 2 times 3 times 5 is 60. The temptation here is to use the common denominator, just multiply the two, 120. And sometimes people do that out of matter of expediency rather than finding the least common multiple. With polynomials, it's crucially important that you use the least common multiple. So when we have something, let's say, here again, ignore the numerators, the denominator here, notice you have the x plus 2 in common between the two of them. The least common multiple only uses it once. It doesn't use it both times, but it uses each of the unique factors, x and x plus 1, as well. Okay, so find the least common multiple between 18m to the m squared and 45m. What would be the least common multiple there? So what is it? Anybody know? Anybody?
So 180.
180? You multiplied the two together? No, you wouldn't have, right? How did you find it?
I see. I messed up.
Okay, so let's do this manually. So it's going to be 2 times 3 times 3 is 18, m squared, and 45m is going to be 3 times 3 times 5, right? M. Now what's in common is I have two 3's that are in common, and then I have, if I write this out as m times m, I have two m's in common here, or I have one m in common. So my least common multiple is going to be, take my common factors, so that's 9 times m, and then take all the unique factors, 2 times 5 times m. And so this is going to be 9 times 2 times 5 is 90, m squared. Okay? Now, I think back in chapter 1 somewhere they talk about least common multiples. If you need a little bit more practice in finding least common multiples like this, I suggest you go back to review that. We're going to be finding least common multiples of polynomials that are factored. So the principle is the same, but it just looks a little different. So first, let's just use 12 and 20. Remember what the least common multiple was there. It was 60, right? Because we have 12 is 2 squared times 3, and 20 is 2 squared times 5. So we use what's in common, which is the 4 times 3 times 5, and we get 60. Now, what we do with that is that we need to multiply this denominator by whatever factor it takes to get to our least common multiple, our common denominator. And since we don't want to change its value, we're going to multiply it by 5 over 5, so that it equals 1. We haven't changed the value for multiplying by 1. So in order to get to 60, we multiply by 5, keep up with that in the numerator. Same thing in the second one. To go from 20 to 60, we have to multiply that by 3, and so we multiply the numerator by 3 as well. And so we get 25x plus 9 over 60. Okay, so let's do it with a polynomial now. 5x over x squared minus 1 plus 3 over x squared plus 2x plus 1. If we factor it first, we can see what's going on. Here we have an x plus 1 in common, and then we have another x plus 1 that's unique here, and an x minus 1 that's unique. So my LCM is the x plus 1 squared times x minus 1. So then in order to go from, this is x minus 1 times x plus 1, to get to that LCM, I'm multiplying it by another factor of x plus 1. Do that to the denominator as well. Then here, I need to multiply it by x minus 1, numerator and denominator. So I have my common denominator. And then I expand. This is going to be 5x squared plus 5x. Actually, I do correct this. I know I do. Yeah, there it is. Okay, so 5x times 1 is 5x, and then I have 3x minus 3, so then I add up my like terms, the 5x and the 3x, and I get 5x squared plus 8x minus 3 over this. Now, at this point, you need to check to see, does it simplify? Now, you can figure that this one does not factor, right, because 5 times negative 3 is negative 15, and what two factors to get to negative 15, we're looking at a difference, has to be 8, and that doesn't happen. Okay? So this is not factorable, therefore this is simplified already. Okay, so here's a few for you. Okay, so that first one turns out to be 3 over x minus 2 and x plus 1. Second one is at 6x minus 1 over x minus 1 is x plus 1, and let's see, the trick here is to do the factoring first. Okay, you got it. Okay, so you do the factoring, and then you can see you have a common factor here, so all you have to do is multiply this one by x and this one by y, and so you get your common denominator, y squared minus x squared. That, of course, factors, and then you have the x plus y in common, so that cancels out, and you just get y minus x over xy. The domain restriction you get from taking out this x plus 1 is going to be x does not equal negative y. So that's one of the few that we've actually had a domain restriction for.